It's MK the guy. In this video, let's talk about barbiturates. Please don't forget to subscribe, like the videos, and share. We are going to introduce our topic, and in the introduction, we are going to talk about the mechanism of action. We are going to talk about the general structure and SAR, how to identify the drug, whether it's long-acting, short-acting, intermediate, or ultra-short-acting. Here we shall give the examples and the structures. We talk about the solubility, acidity, and salt formation plus the pKa. We also talk about the incompatibilities, we shall see them. Inactivation processes, the uses, adverse drug reactions, and some of the drug interactions. We talk about the metabolism of some drugs and the general metabolic pathways. Then we talk about the general pharmacological actions and other pharmacological actions. Yes, it's MK the guy. Please don't forget to subscribe, like the videos, and share. Let's go. There are the prototypes of the CNS depressants. They are the prototypes. These drugs, they are very toxic, so they are replaced by safer drugs. Those are the benzodiazepines. Except a few specialized uses, as we shall see here in the uses. But mostly these drugs, they are replaced by benzodiazepines. These drugs, they were used extensively as sedative, hypnotic drugs. But we are replaced by benzodiazepines, though some few cases. Let's talk about the mechanism of action. For the mechanism of action, these drugs, they bind at the GABA A receptor. And the site of binding is different from that of the benzodiazepines. And after binding, these drugs potentiate GABA. They potentiate the GABA inhibition by increasing the lifetime opening of the chloride channel. So they are GABA potentiators. At high concentration, these drugs can mimic the action of the GABA itself. So they are, at high concentration, they are GABA mimetics. They can lead to the chloride influx in absence of GABA. They can lead to chloride influx in absence of GABA at high concentration themselves. So they act as GABA itself. Here, they just potentiate the inhibition of GABA. GABA is the one which leads to the chloride channel opening. But here, at high concentration themselves, they can lead to the chloride influx. Also, at high concentration, these drugs can also inhibit the voltage gated potassium and sodium channels. They can inhibit these channels. Barbiturates also, they can displace the glutamate depolarization of the membrane. by binding at AMPA receptors. So barbiturates can inhibit all these. They can also inhibit the calcium dependent production or release, calcium dependent release of neurotransmitter. All these. Let's talk about the general structure and SAR. Yes, MK the guy. About the general structure, barbiturates, they are from barbituric acid. And this is the structure of the barbituric acid. This is the barbituric acid. As you can see, it is the pyrimidine. So it is, this is position 1, this is 2, this is position 3, 4, 5, and 6. At position 2, 4, and 6, we have oxygen atoms. So we have, it will be called 2, 4, 6 trioxo. And all the atoms, they are saturated, so it will be hexahydropyrimidine. It is 2,4-trioxo hexahydropyrimidine. This is the barbituric acid. Barbituric acid itself cannot cross the blood-brain barrier. Cannot cross due to its lower pKa. It has lower pKa. At physiological pH, this barbituric acid ionizes, and most of the drug will be ionized, so it cannot cross the blood-brain barrier. And we are going to see more why. For the general structure of the barbiturates, they are from barbituric acid. So this is the general structure. At position 5, we substituted all the hydrogen atoms. Remember, here we have 2 hydrogen atoms. This is position 5. So let's this one be called R5 prime. Also, this position, at N position, we can substitute the hydrogen. So this is the general structure for the barbiturates. And it's called 5,5 di-substituted. 5,5 di-substituted barbituric acid. Barbituric acid. Now, let's talk about the SAR. For the SAR, we are going to begin with this position 5 and see why we must substitute all the hydrogen atoms. Position 5, all the hydrogen atoms at position 5 must be substituted. Why should we substitute all the hydrogen atoms at position 5? This is because if one hydrogen is present, if there is one hydrogen, if you substitute one, we can lead to tautomerization. And tautomerization can result into the formation of the trihydroxypyrimidine substituents. So in case we have hydrogen here, what can we form? We can have this. Here there is hydrogen. Here we have R and a hydrogen atom. In case this is also hydrogen, as in some drugs, as we are going to see. Here, remember, tautomerization, we are moving the hydrogen atoms, but the structure remains the same. We can have this. This hydrogen, this nitrogen can form a bond here. When it forms a bond, this hydrogen goes to the oxygen. Also, this one can form a bond here. Can form a bond here, and this hydrogen goes to this oxygen. Also, this hydrogen, here we have oxygen atom. This hydrogen can be lost to form a bond here, and it goes to the oxygen. This is the trihydroxypyrimidine, and this one has a lower pKa, approximately about 4. Now, this pKa means at physiological pH of 7, around 7, this drug will ionize. So we shall form this. We can form this. Can form this, and this one is too hydrophilic. It is too hydrophilic, means that it cannot cross the blood-brain barrier. So this one will not have the pharmacological role. It's the same for the barbituric acid. Here we can form this, and this hydrogen can form also this. Also, this one can form this OH. So it's the same thing. This one cannot cross the blood-brain barrier because it can ionize. It can also form the trihydroxypyrimidine, and this one has lower pKa and it cannot cross the blood-brain barrier. So we shall not have the hypnotic activity or the sedative activity of this drug will not be there because the drug cannot reach the CNS. Much of the drug will be ionized and very little will be non-ionized to cross the blood-brain barrier. This is one. Position 5 must be substituted. Let's see other SARs. Yes, for other SARs, as we say that for position 5, it must be the hydrogen atoms must be substituted, all of them, because these drugs are acidic, and if the pH is higher than the pKa, means that the drug will ionize, so it will not cross the blood-brain barrier. Also, at position 5, addition of alkyl or the phenyl groups, they increase the lipophilicity. Increase in lipophilicity increases the potency and also to reduce the duration of action of the drug because of the redistribution. The onset of action will also be reduced because the drug can easily cross the blood-brain barrier. This increases also the protein binding. Additional alkyl group or phenyl group will increase the lipophilicity, potency, or decrease the duration of action. Onset of action will also reduce and increase in protein binding. And this for the phenyl or the ethyl group or propyl will provide the almost same activity or the same lipophilicity. Then when you go on increasing the chain, increasing chain will increase more than these groups. Again, increasing branching of the chains increase the lipophilicity more than the straight chains. Also, formation of double bonds or triple bonds will increase the lipophilicity more than just branching, as we are going to see the different drugs. Still at position 5, this increase in the branching and double bonds or increase in chains will also increase the metabolism. There is easy metabolism of these drugs. So this one reduces the duration of action due to increase the metabolism. Thirdly, the total number of the carbon atoms at position 5, either this 5 or 5 prime, the total number of carbon atoms at that position should not be less than 4. So it should be between 4 but not greater than 10. 4 to less than 10. The total number of carbon atoms here for optimum binding or for optimum activity. So that's another SAR here. Again, at that position, addition of halogens are the alkyl chains. This one will increase the lipophilicity and also will increase the potency. But addition of hydrophilic groups or the polar groups, like the OH groups, the amine groups, the carboxyl groups, these hydrophilic groups. This one reduces the potency. Reduces the potency. Another SAR here, we have this carbon. This carbon can be chiral, but it can only be chiral in case this R3 is substituted. If it is not substituted, when it is hydrogen here and here it's a hydrogen, this part cannot be chiral, and can only be chiral if this one is substituted and these groups are not the same. If they are the same, it can't be chiral. Remember, a chiral carbon should be having 4 different atoms attached to it. If here it's a hydrogen, means that this side and this sides are the same, unless this one is substituted. So we must have a substitute here, and also these ones should be different for it to be chiral. And chirality will give us the isomers. But these isomers, they almost have same activity. All the isomers will give us same hypnotic activity. But what will be different, maybe it's the metabolism of these drugs, but activity will be the same. Another thing, here, only one of the substitutes either this or this, one of them may be cyclized, maybe cyclic, but not both. If both are cyclic, there will be no activity. So either one of them or none should be cyclic or aromatic. Now let's go to position 1 and 3. Yes, about position 1 and 3. This position, this nitrogen can lose this hydrogen. So mean that it is acidic. This drug is acidic. It's like this. Position 1, this nitrogen can lose the hydrogen and becomes nucleophile. So meaning that this one is responsible for the acidity of the drug. Meaning that substitution at N1, this N1 leads to decrease in the acidity. Substitution. Alkylation, like methylation of this position, lead to increase the lipophilicity. It's the same. In case this one is also a hydrogen atom, it can behave in the same way like this one. As we shall see, some drugs, this one, it is a hydrogen atom, meaning that it is also responsible for the acidity of the drug. And substitution leads to the decrease the acidity. Alkylation can increase the lipophilicity of the drug. And this one, of course, reduces the duration of action due to redistribution. So this is position 1 and 3. Now, when it comes to position 2, for position 2, in case the oxygen is substituted with the sulfur atom, the S here, this one increases the lipophilicity. And increase in lipophilicity, of course, decreases the duration of action and also the onset of action. So we shall see drugs like thiopento. We shall see thiopento. But substitution at carbon 6, this carbon 6 and carbon 4, if they are all substituted with S, this one reduces the activity. mean that you can only substitute one for optimum activity. So generally, that's the SAR of these barbiturates. Also, this position 5 also decreases the acidity of the drug, as you can see. If we substitute the hydrogen atoms, mean that we are reducing the acidity of the drug. We are removing the hydrogen atoms, but it increases the lipophilicity, as we saw. Let's see now how to identify whether a drug is long-acting, short-acting, or intermediate, or ultra-short